I said like, okay, I put like a nice giraffe texture on that, and then you say like, maybe we have a small one or like some small other animal, and you can look at the, like, okay, like if they have the same Euler characteristic, or what you do is like you do triangulations of them, which in a computer vision is actually a very natural thing to do. So you build up your objects out of triangles, and then if you calculate the Euler characteristics of both of them, you know there exists a bijective map between these two surfaces. And if you have a nice bijective map, what you can do is you can map the texture from this one object onto here to get like the texture transferred from this giraffe to a whatever other animal that is over there. So that's one way to use that, for example, in computer vision. And usually, like the first example over there is like in computer vision, what happens usually is, if, for example, if you want to triangulate a face, is that you need like adaptive mesh. You usually put a lot of triangles where you have a lot of curvature. So that's like displayed here, is that usually if you do it like very coarse-grained, then you kind of lose the geometric features. But if you are a bit more adaptive and like put smaller meshes over where you have a lot of curvature, then you usually get like quite a good result of your original picture. So that's also one application of curvature back to areas like computer vision. So that's one example of like where we can use triangles and triangulation outside of mathematics. Okay, so the last step that I have to tell you is what is the relationship through the Euler characteristics and the number of holes. So that's like something that is not clear, right? Like because you had like, what is this number, the points, edges, and faces with this strange minus sign? What does this have to do with the number of holes that you have in an object? And the claim here is the following, that the Euler characteristic is minus 2 times the number of holes minus 1. So the proof is kind of by induction. So what we have seen already is that for the sphere, the Euler characteristic was 2, which would be okay because the number of folds of the sphere is 0. So in this case, we just get 2. So that's in a the number of folds would be 0. For the torus, we have seen that chi was 0, which is also correct because the number of folds would be 1, so the right-hand side gives you 0. So it's already there. So the general case follows them from this construction that if you have your surface and it might have like already some kind of numbers of folds that you already understand, and you would like to add one more, what you can do is we just take a torus and we would like to glue them together. So what you do is you take some triangle in your surface, and you take one triangle in the torus, and then you start gluing them together on these triangles. So you have the triangles, and then you put some glue on them, and then you stick them together. So under this operation, the resulting surface has two faces less. Then, the number of faces of S plus the number of faces of the torus. So if you glue them together, then obviously like the faces get like eaten up, and they're like inside now. So like we get like two faces less than what we had originally. And also the edges and the vertices are like eaten up, but that's actually doesn't matter too much. So and 6 vertices and edges less. But this one actually doesn't matter too much, because in the Euler characteristic, the number of vertices and the number of edges they cancel each other. So the effect in total is that the Euler characteristic from the S plus the T glued is equal to the Euler characteristic of S plus the Euler characteristic of T minus the two faces that we left. And the Euler characteristic of the torus is 0. So what you end up with is saying that if you add one hole by gluing a torus onto it, your Euler characteristic goes down by 2. And that's actually what this formula is saying, is that if you increase your number of holes by 1, then the Euler characteristic goes down by 2. So that verifies this formula over here, that the Euler characteristic is a good measure for the number of holes there. One remark is that so far we only talked about the triangulations of objects that don't have a boundary, but things get a bit like more complicated if you have boundary. So let's say side remark with boundary. And there we maybe just look at like one particular example of like the disk with boundary. So that's the solid disk, and the boundary is of course the boundary curve that we have. And one triangulation of that one maybe looks like then yeah, so it's kind of so in this case you get a triangulation of the solid disk, and in this case, if you calculate it, you might end up with something that is not even. So this formula over here shows you that you always have like an even number for the Euler characteristic in terms of the holes, but that was really relying on the fact that we talked about surfaces that don't have the boundary. So with boundary, you might end up like some other terms there. So it's really this one is only true for surfaces without boundary. Okay. And with that preparation, we can now come back to our Gauss-Bonnet theorem. So the global Gauss-Bonnet theorem that says that for every compact oriented surface S without boundary and with area element K, dA, and Gauss curvature K, we have the following, namely that the integral of the total Gauss curvature is given up to normalization by a factor of 2 pi by the Euler characteristic of the surface. So that's the same formula that I had at the beginning, using the number of holes, but slightly more mathematically, it's really the Euler characteristic that is written there. Just side remark, there's also a version that has some correction terms if you allow boundary. Okay. So how do we now get this Gauss global version of Gauss-Bonnet from the local version, and this whole discussion with vertices and edges and faces of triangles? So what is the connection there? the idea is we just decompose our surface in triangles. So we have a bunch of triangles that we enumerate from 1 to some number, and by one of the points that are erased over there, we can assume that each of these triangles is covered by a single chart. So that means in particular it has a nice oriented frame, and that means that we can apply our local Gauss-Bonnet to it. So what we end up now is then we have the surface integral over the Gaussian curvature, the thing that we want to calculate, and that's clearly the same thing as the integral over a triangle, and then just sum up the contributions that we get from all the triangles. And then we can apply here, we can apply the local version. So what we end up with still write that. The local version gives us then the following, that we can apply over here. We get minus the integral over the boundary of the geodesic curvature, and then minus pi plus the sum of the angles. Phi 1 plus phi 3. So that's the boundary of the J triangle, and here these are the angles in the triangle. So maybe we give them also a number J. So what we end up now is, like, if you decompose all of that, what we end up with is like sum over the boundary terms, sum over the pi's. That will be easy because it will be just like the number of faces that we have in the triangulation, and then this one will be the angles. So we now need to analyze all of these sums separately. So for the sum, so what we have, the sum over the boundaries, the geodesic curvature. There we are, what do we get there? So clearly, like the Gaussian curvature, geodesic curvature of one of these triangle boundaries, there might be something. We don't have any assumption that we can like always get geodesic triangles. So that might be some number. But the nice part is that from the orientation, if you have like one triangle and we go around it like this, and we have a different triangle, we said that they need to be oriented in a compatible way. So what happens is that if you walk around like this, then on a shared edge, you work around actually the opposite direction. And that happens like on every case. So on every edge, you get like always walking around in opposite directions. So here, we actually get 0, since for two triangles that share one edge, the edge has the opposite orientation in the above sum. So each edge is like counted twice, and once we get it with a plus sign and once with a minus sign. So if you take the sum over all of that, we get 0. And so that's this sum. And now we have the sum over all j's of the interior angles. And there the trick is that if you have triangles which meet at like a common vertex, if you have something like that, then if you now sum up all these contributions around one vertex, you always get up with 2 pi, because you go around once. So if you sum up this angle of this triangle, this angle here, and this. So if you sum up all the angles around like a given vertex, you always end up with 2 pi. So if you have if you have a vertex, so the idea here, instead of that we take the sum over all triangles, we actually just take the sum over all vertices, and then we get like 2 pi every time. So what we end up there is that we end up with 2 pi times the number of vertices. Okay, so now we can go back here to get our integral. So we write it like this. So the first one is that we have the sum over all boundary terms of the geodesic curvature. As we discussed, that one gives us 0. Then we have the sum over all j's. For each one we get a constant, so that's minus pi. So we get minus pi times the number of faces, or the number of triangles that we have. And then the last contribution was we get the sum over all of the interior angles. And as we discussed just now, that gives us plus 2 pi of all the vertices. So, well, that's not like exactly what we want. We want something with edges. So what is the relationship between faces and vertices and edges? Is the following, that side remark is that each face has 3 edges. So each triangle just have like 3 edges, that's clear. And each edge is shared by 2 faces. So if you have an edge, then you have a face on the right and a face on the left. So that in formulas means that 3 times the number of faces equals to 2 times the number of edges. And writing that equation a little bit differently means that minus the number of faces, which we could write as 2 minus 3 times of the number of faces, is the same thing as 2 times the number of faces minus 3 times the faces, which would be 2 times the edges. So we get 2 plus the edges. Sorry, with a minus sign because of that minus sign. So what we get now is that minus the number of faces we can write as 2 times the number of faces minus 2 times of edges. So that's nice because we had here the number minus pi of number of the faces. So we get minus 2 pi, and then we have the 2 pi also here. What we now get is, here we have the number of faces minus the number of edges, and then we get one more coming with a plus, which is the number of points of vertices. And that was exactly our Euler characteristic. Sorry, there's no minus sign there anymore. So we get our Euler characteristic. And that's the proof of the Gauss-Bonnet theorem. So there were, like, to summarize, like, the discussion for today, were like twofold. There's like the one was that we proved that for like a small triangle, and for that we essentially only used Stokes' theorem to say like that the total curvature of the triangle can be given in terms of like something that is measured around the boundary term. So that we had like that was the result for the triangle. Then we cut out our surface a little bit like here, and we made it like consisting out of triangles, and then we just needed to sum up all of the contributions that we get from each of these triangles. And there were like 2 ingredients. One of them was that the edges terms like cancel because they go in opposite directions, and then some a bit more combinatorial argument with the number of faces, and like this one here, that the number of edges and faces is connected. And that gives us then the connection to the Euler characteristic, and as we explained before, the Euler characteristic is essentially the number of holes, but just like shifted by 1. So that gives us now the statement of the Gauss-Bonnet theorem. And for the remaining part, I would like to mention some applications. So the first one is that if, for example, the Gaussian curvature is positive everywhere, then, or maybe the other way around, like what we are seeing is that the Euler characteristic can be 2, 0, and then like decreases to get minus. So that means if that right-hand side, left-hand side is positive, then also the Euler characteristic has to be positive. So that means the Euler characteristic has to be a 2. So every compact surface has curve K strictly positive, which is like everywhere positive, this one has to have Euler characteristic of S equals to 2. And by the previous discussion, that means exist a bijective of S onto the sphere. So whenever you have a surface and you measure that the Gaussian curvature is positive everywhere, then you know up to like a bijective map, it's like the sphere. So it's like a sphere which is like deformed and like maybe gets like a bit like, for example, ellipsoid or something. So that would be it's like the first result that we get immediately from the theorem. Then one statement, but I don't have the time for that. You can say that every two simple geodesics on S with strictly positive Gaussian curvature, they have to intersect. So there, if you have two geodesics on the surface, and the surface has positive Gaussian curvature, then these geodesics have to intersect somewhere. And the idea is that essentially by the first one, it's enough to look at like the sphere. And if you don't have like on the sphere, you would have two geodesics which don't intersect, and you would have kind of like two curves that don't intersect. Then you have an annulus, like this middle part here, and you can essentially apply the Gauss-Bonnet theorem on each of these parts, and then you get a contradiction that some of them, like essentially in the middle part, would be 0, and that contradicts that the Gauss curvature has to be positive on that part. And then the Gauss-Bonnet theorem tells you that you can't have that because, by assumption, the boundary terms are geodesic. So you don't get any boundary contributions, and the middle part has positive Gauss curvature, but that can't be the case. So that would be like a rough sketch of like why that can't be the case. Okay, and the following statement is properties are equivalent and the first one is that they exist a smooth bijection to the torus. So the question now, not with the sphere, but we assume that we have a smooth bijection to the torus. That means by this discussion that we had before, the Euler characteristic of S has to be 0, because it has to be the same Euler characteristic as the torus. And there's a statement that this one is equivalent to the fact that there is a non-vanishing vector field on S, which in the case, if you have a smooth bisection to the torus, then okay, then your surface is essentially the torus, and on the torus you clearly have a vector field which just goes around one of these circles that you have, like the torus made out of two circles, and you can just take one of these non-vanishing vector fields, which is just one of the rotations. So if that's your torus, then you can just take the vector field, which is turning around one of these. And I'm mentioning this statement because there is actually a nice proof of the whole Gauss-Bonnet theorem that uses vector fields. So the idea here is that, like the Gauss-Bonnet theorem, tells you also certain things about vector fields. What we had was the Harry-Bohr theorem that was saying there's no vector field on the sphere that has like at least that's nowhere vanishing. So every vector field on the sphere has to vanish somewhere. And that's very much related to this statement, is that there is some nice, interesting combinations and connections between the Gauss curvature and if there's like certain things like vanishing vector fields. And there's actually a proof of the whole Gauss-Bonnet theorem that only analyzes vector fields. So what we had was like the connection forms and then Stokes theorem and all of that. But there is a nice proof that also goes only via certain things that are called indices of vector fields. So you get some dynamics of vector fields on surfaces. You can also study them in terms of the geodesic curvature and the Gauss curvature. And I think that wraps it up, not only for this lecture, but also for the whole class. I hope you enjoyed it. I hope you like geometry more now than you did before. I definitely hope you understand geometry better than you did before. And with that, I wish you good luck with the exam. And we will see each other then next week at the exam. I will be there. Otherwise, see you then. You mean like from the, you don't understand the frequency of the assuming that you have like that you have like we assume you have two servers here, here, and you assume that you don't need this. You have a picture like this. That you have like one here, and then you apply So the idea is, as I said, you have like take a triangulation of this S and the tau, and then you glue them together at like one face, like on one triangle. Yeah, it's only like the triangles. Like you take like the triangle and you put like glue on it, and then you put them together. And then you count the number of faces.
After glue, the intersection of the S and T is this triangle.
So you glue them together. Like you have. So, like assuming you put glue on here, and you put glue on here, and then you plug them together, and then you calculate like what is the triangulation of like the common thing. If you glue them together, then what happens is like that, like now this face and this face they disappear, right? And that means that if you calculate the number of faces, you get like 2 less because that's where you glue them. And the number of edges and faces and points also changes, but like this one is like the same, like it changes by 6 vertices, and like so that doesn't change. So the Euler characteristic of this new object where you glued is like 2 less than the object that you had, like the torus and the original object. So what you add up is like if you glue a torus on there, the Euler characteristic will change by -2. And that means that like picture-wise, like a torus has one hole. So if you add one more hole by gluing the torus, so if you have like one hole in here, and you glue that to a surface, then you add one more hole.
If there is a hole on which,
so you don't glue at like the hole, but you have like here, like for example here this one is one hole, right? So now you take a torus and you glue the torus against it here. What you end up with is like one hole here and another hole here. So the glued object has 2 holes, and as we just discussed, has Euler characteristic that is 2 less. That's the idea. Does it make it clear?
the glue object's chi is the original chi plus the chi of tolerance is 0, and then but if the number of the the number of the holes of the origin surface is 2.
Yeah.
And then the glue object with 3 holes.
Yes.
2 plus chi.
Yes, so then that means that the chi of the thing with like 3 holes is the chi of the thing with 2 holes minus 2. It's like what we are. In our shortcut, the chi of s plus 2 equals chi of s minus 2. And the number of holes of s plus t equals the number of holes of s plus 1. Because you do a drawers and you calculate the chi of the original object. So that means that adding one hole gives you minus 2 in order to make this. Vice versa.